High-performance machine learning inference relies heavily on a deeply entrenched ecosystem of C and C++ compute stacks. Frameworks and developers default to highly optimized hardware-specific libraries, like NVIDIA's CUDA or OpenBLAS, to process the massive mathematical workloads required by neural networks. When developers write in higher-level languages like Python, they are actually just interfacing with these C++ kernels through foreign function interfaces. The top-level language issues the commands, and the C++ backend does the heavy lifting. This creates a structural barrier for memory-safe concurrent systems languages like Go. To access these accelerated mathematical libraries, Go developers are forced to use CGO, a tool that acts as a mandatory bridge between the Go runtime and native C++ execution speeds. We can see the problem in this architectural stack. CGO introduces infrastructural friction. Every time a Go routine calls into the C library, the scheduler must lock an operating system thread, transition the execution stack, and manage garbage collection barriers. In high-frequency environments, stripping away these intermediary layers removes the C application binary interface overhead. OpenFluke developed the Loom engine to solve this exact problem. Loom is a deterministic neural virtual machine built entirely in pure Go, establishing a direct hardware pipeline. The engine completely bypasses the C application binary ecosystem. By pairing custom Plan 9 assembly code with a radical spatial topology, Loom is designed to test if pure Go can execute matrix operations natively without inheriting the friction of cross-language dependencies. At the mathematical level, matrix multiplication dictates the speed of any neural network. Naive implementations carry an asymptotic time complexity of O(n cubed, meaning the computational load scales aggressively as network size increases. A standard central processing unit executes operations sequentially. When dealing with large arrays of floating point numbers, this scalar approach hits a memory wall. The processor's arithmetic logic unit sits idle, waiting for the system to fetch numbers from memory one by one. This diagram outlines the hardware solution: single instruction, multiple data, or SIMD. Instead of loading two single numbers for an addition operation, modern processors use expanded registers, like the 256-bit AVX2 YMM. This widens the memory bus, loading 8 numbers concurrently. But the Go compiler presents a software limitation, lacking auto-vectorization passes to natively utilize these hardware instructions. The Loom engine navigates this by writing raw Plan 9 assembly code. Developers bypass the compiler's limitations by directly mapping vectorized instructions, like v-add-ps, to custom opcodes, forcing the CPU to process the matrices in massive blocks. For highly advanced instruction sets, such as the AVX512 VNNI used for sub-byte quantization, the Go assembler lacks native mnemonics completely. Accessing these requires developers to hard-code raw machine opcodes into the assembly files using byte directives. Writing direct SIMD assembly in Go completely bypasses the language's native bounds checking overhead and sidesteps the latency of a CGO context switch. It is the necessary path to extract bare metal performance from the hardware. To test the efficiency of this approach, OpenFluke benchmarked a purely spatial tiled multi-core execution against the heavily optimized Plan 9 SIMD implementation. This table displays the dense 3x3x3 CPU benchmark, comparing latency across numerical types. In the float32 row, SIMD optimization reduces execution time from 3.39 milliseconds down to 893 microseconds. That is a 74% reduction in total latency. But notice an anomaly. Float16 and bfloat16 actually exhibit higher base latencies in the scalar tiled configuration than the larger float32 type. This occurs due to a specific hardware constraint. Older x86 platforms lack native 16-bit scalar math instructions. To process these arrays, the CPU must actively unpack the 16-bit floats up to 32-bit for the calculation, and then downcast them back to 16-bit to finish. Transitioning to the SIMD processing path completely eliminates this unpacking overhead. For bfloat16, vectorization drops the latency drastically, yielding a 2.5 times speedup. As the architectural complexity of the model scales up to billions of parameters, these microsecond reductions compound. Vector optimization is a strict requirement for Go-based edge inference. With node-level MAT optimized, the engine requires a structure to route the resulting data efficiently. Standard neural network frameworks treat this structure like an assembly line. They process multidimensional arrays through a strictly linear unidirectional pipeline, passing data sequentially from one distinct layer to the next. This models Loom's volumetric tiled-tensor dispatcher. Rather than a flat pipeline, it conceptualizes the neural network as a living, three-dimensional spatial grid. Layers are situated across z, y, and x coordinates, mapped using this specific offset formula. Because the structure is volumetric, the engine utilizes remote links. A layer at one coordinate can draw input tensors directly from a distant coordinate across the grid, rather than pulling from the layer immediately preceding it. Supporting dynamic paths and dozens of layer types typically introduces severe processing delays from runtime type checking. Loom resolves this with a dispatcher pattern, explicitly decoupling the spatial traversal of the grid from the actual mathematical execution. The traversal loop manages the coordinate indices, keeping thread divergence minimal. While it does this, the hardware driver and CPU prefetcher load the next tile's weights into high-speed memory precisely as the current mathematical kernel executes. Separating the coordinate loops from the math sets the architecture up for GPU and web GPU execution. Low-level graphics APIs can inspect groups of identical layer types and launch a single batched compute shader, reducing CPU to GPU driver calls. This volumetric layout breaks the rigid constraints of traditional feed-forward backpropagation. Networks can route information backward across the grid to learn locally, enabling biological-style target propagation right on the device. When firing all these dynamic layers simultaneously in Go's highly concurrent Go routine environment, the system faces an extreme risk of race conditions, where multiple threads attempt to read and overwrite the same data points at once. To prevent this, Loom uses a step mesh engine. Instead of evaluating the network sequentially, it evaluates based on discrete clock cycles, modeling actual electrical firing patterns. This visualization shows how the system safely manages clock cycles using a strict double buffering pattern. The engine maintains two isolated memory spaces. During a cycle, layers pull inputs from the blue buffer and write computed results to the green buffer. The engine waits for every parallel Go routine to finish its computations. Only after all layers have finished firing does the system physically swap the memory pointers of the two buffers, preparing for the next clock cycle. This double buffering mechanism completely eliminates race conditions. It ensures the massive parallel tile dispatch can safely execute complex temporal feedback loops directly in Go. To maximize efficiency across various hardware constraints, the Loom dispatcher maintains bit-level mathematical parity across 21 discrete numerical data types within a single binary. This represents the core memory lifecycle manager, called the weight store. It retains an immutable, authoritative master copy of every network weight strictly in high-precision 32-bit floating-point format. When deploying to memory-constrained edge environments, the network executes polymorphic morphing. The engine dynamically recompiles the numerical representation in real time down to a low-bit format like int8 for execution, leaving the master copy untouched. If the model requires training updates, the system applies the gradients directly to the float32 master. The dispatcher automatically clears out all low-bit caches, forcing a fresh requantization on the next forward pass. Loom captures this optimized state natively using the entity checkpoint format. Instead of unpacking weights back to full memory formats to save them, it packs sub-byte types directly to the disk, exactly as they exist in RAM. By utilizing 1-bit binary precision, a massive large language model shrinks by 98.4%. It fits onto a USB stick or low-end mobile phone, executing entirely offline. We can now see the entire architecture functioning as a cohesive unit, a volumetric, double-buffered 3D grid running non-destructive sub-byte formats powered entirely by a custom SIMD dispatcher. The Loom engine removes the CGO dependency from the stack. It achieves the hardware utilization of C++ while maintaining the memory safety and concurrency benefits native to Go. The engine executes with bit-exact reproducibility and flat, predictable latency because it generates near-zero garbage collection pressure during heavy computation. High-performance deterministic AI inference is no longer restricted to cloud-dependent infrastructures wrapped in heavy CABI pipelines. Networks can now exist fully localized on consumer devices. By architecting this engine from first principles, OpenFluke demonstrates that pure Go provides a robust, self-sufficient substrate for the deployment of sovereign edge artificial intelligence.